Hello to everyone. My name is Aleksa Stankovic and I come from KTH Royal Institute of Technology, which is based in Stockholm, Sweden. I will be talking about Max-3-Lin over non-abelian groups with universal factor graphs. This is a joint work with Amey Bhangale, who is working at University of California, Riverside. Let me start by discussing the outline of this talk. First, I will discuss approximability of Max-3-Lin over general groups. Then, I will introduce the notion of universal factor graphs and highlight some of the research on this topic. Subsequently, I will tell you about our result. I will finish the talk by discussing some of the techniques used in this work. Let us begin. In the Max-3-Lin problem over F2, we are given a system of equations in which the terms are 0, 1 valued and addition is taken mod 2. The algorithmic goal is to maximize the number of equations. If all equations can be satisfied, then you can find an assignment using Gaussian elimination. Otherwise, consider an algorithm that picks a random assignment. Every left-hand side in the instance will be either 1 or 0 with probability 1/2, and hence half of all the equations are satisfied in expectation. This is rather simple procedure, and it is natural to ask whether there are better algorithms than this. Hosted in his seminal work showed that, among other things, beating the random assignment is NP-hard. In particular, Hosted showed that for every epsilon greater than 0, it is NP-hard to distinguish the following two cases. More than 1 minus epsilon fraction of equations can be satisfied. At most 1/2 plus epsilon fraction of equations can be satisfied. For the sake of brevity, we usually just say that Max-3-Lin is 1 minus epsilon 1/2 plus epsilon NP-hard. We refer to the term 1 minus epsilon as completeness and to the term 1/2 plus epsilon as soundness. Let us now discuss Max-3-Lin over a general group G. In this case, we have equations of form x1 times a times x2 times b times x3 is equal to h, where the terms take values in some fixed finite group G. Let us remark that we think of G as being fixed and of instance as increasing in size. We split our discussions into two distinct cases, when G is abelian and when G is non-abelian. Let us discuss abelian case first, as you already saw one example with G's being equal to the F2. Even for general abelian group, satisfiability is easy to check, again by using Gaussian elimination. Also, random assignment satisfies 1 over size of G fraction of equations in expectation. Previously mentioned seminal result of Hosted gives a matching hardness, and in particular shows that Max-3-Lin G is 1 minus epsilon 1 divided by size of G plus epsilon NP-hard. Let us discuss non-abelian G now. The situation becomes very different from any group G, and in particular, deciding satisfiability becomes NP-hard, as shown by a result of Goldman and Russell. We still have 1 divided by size of G approximation given by taking a random assignment. However, this can be improved on satisfiable instances by an elegant algorithm. Let us illustrate the idea on G equals to the S tree. In particular, we consider G to be the set of all permutations of a 3-element set, and the group operation is composition of permutations. We use sign of G to denote the sign of permutation G. Let us now discuss the algorithm. We start with some instance f, which has one of equations as shown in the box. Let us now take sign on both sides. We can then pass with sign through compositions. Then we can calculate sign of constants. Finally, let us rename sign of xi with yi and observe that yi take values in -1, 1 set. Let us now continue discussing our algorithm. We have arrived at a system of equations with yi being ±1 valued, with multiplications between them. But this is actually a system over F2, which is perfectly satisfiable and abelian. And hence we can find yi using Gaussian elimination and hence get information on signs of each xi. Consider now taking xi to be a random permutation of sign yi. Since there are 3 permutations of each sign, we will satisfy the third of equations in expectation. For a general group, using a similar idea of reducing to an abelian system gives us 1 divided by the size of commutator subgroup fraction of equations in expectation. I will not tell you what commutator subgroup is. However, it's usually smaller than G. And in this case, we get a better approximation than 1 divided by the size of G approximation, which simply takes a random element from G. Let us give an overview of Max-3-Lin over non-abelian groups on unsatisfiable and satisfiable instances, and in particular their approximation and hardness. For unsatisfiable instances, we have 1 divided by the size of G approximation given by considering random assignment, which is matched by a hardness result showed by Engebretsen, Holmarin, and Russell. For satisfiable instances, the approximability of aforementioned algorithm is matched by a recent beautiful result of Bhangale and Kott. The hardness results discussed previously apply only to worst-case instances. In particular, we know that some instances are easier. For example, bounded degree instances, that is, instances in which the number of occurrences of each variable is bounded by a constant. Another example is given by instances whose factor graph has bounded tree width. I will tell you soon what the factor graph is. Given these examples, it's natural to ask whether it is the case that we can always extract useful information by knowing the structure of an instance. However, in order to study this problem, we need to formalize what structure means, which we do by introducing factor graphs. Well, factor graph essentially tells us how variables are connected in an instance. So, in particular, factor graph is a bipartite graph with vertices being variables and constraints. We connect each constraint with variables appearing in that constraint. For example, C1 is connected to x1, x2, and x3, and we can similarly fill the rest. The only information about f not contained in a factor graph is information about constants ai, bi, and hi. Hence, we can ask what makes Max-3-Lin over G hard. Is it the structure of the factor graph? Is it the details about constants? Is it maybe both together? As we have seen before, factor graphs can be a factor in making instances easy. But let us take the opposite view and ask if there are factor graphs, one for each size of instances, which do not make the task of approximating the optimal value any easier. This study was initiated by Fage and Joseph, who introduced the notion of universal factor graphs and universal factor graph hardness. Let us now give a definition of universal factor graph hardness for Max-3-Lin over G. We remark that the definition can be made for a much more general family of problems. Max-3-Lin over G is C, S U of G NP hard if for each instance size we can fix a factor graph Gn such that for Max-3-Lin over G, restricted to instances with these factor graphs, it is still NP hard to decide whether at least C fraction of equations can be satisfied, at most S fraction of equations can be satisfied. Observe that the first point corresponds to completeness, while the second point corresponds to soundness. As we have mentioned, factor graphs can be defined on more general problems, and Fage and Joseph consider Max-3 set for which they gave 77 divided by 80 plus epsilon universal factor graph hardness. Joseph furthermore showed that all APX hard Boolean max CSPs remain APX hard in universal factor graph setting, although with worse constants compared to the general case. An elegant result of Austrian, Broncoin, and Hostad gives us optimal hardness for many problems, including Max-3-Lin G over abelian G. That is, this problem is 1 minus epsilon, 1 divided by size of G, UFG NP hard. Max-3 set is 1, 7 divided by 8 plus epsilon, universal factor graph, NP hard. They also give optimal universal factor graph hardness for CSPs over predicates supporting a pairwise independent subgroup, building on the work of Sion Chan. However, until now there were no UFG hardness results for Max-3-Lin in non-abelian setting. We build on the previous results by giving optimal hardness results with universal factor graphs for Max-3-Lin in the non-abelian setting. In particular, we prove the following theorem, which gives universal factor graph hardness of almost satisfiable instances. For every epsilon and any finite non-abelian group G, Max-3-Lin over G is 1 minus epsilon, 1 divided by the size of G plus epsilon UFG NP hard. Furthermore, we also give a UFG hardness theorem for satisfiable instances with optimal soundness parameter. There is another interesting side of our result. In particular, we get nicer instances. More specifically, we are able to remove constants appearing between variables, as well as inverses of variables which appeared in work of Engelbrechtsen and others. This makes our instances more structured, and since we are working with hardness, our result is stronger than the previous two. Let us now compare our proofs to the previous works. The main difference from the work on perfectly satisfiable instances done by Bhangale and Kott comes from the fact that we need to handle universal factor graphs, which forces us to suitably generalize relevant lemmas from this work. Apart from these lemmas, the proof mostly goes along the same lines as BK20. However, our proof has more differences to the previous result on almost satisfiable instances. In particular, removing inverses requires us to use a new PCP test, which is arguably more natural, and hence subsequent analysis is completely new and more subtle than the previous one. The main difference to the universal factor graph result in abelian setting consists in using Fourier analysis for general groups and finer level of detail used in the analysis of Bhangale and Kott. If G is abelian, different parts of the proof discussing non-abelian part become trivial, and our results reduces to the previous work completely. The central object we are interested in is a function f mapping from G to the power of n to G. For those familiar with label cover reductions, let us remark that f is intended to be a long code of a label L, which is in range between 1 and n. Due to our setup for universal factor graph hardness, we need L to satisfy some constraints which can be expressed as pi of L is equal to the bi, where I is ranging from I to R, and bi are bits and pi are functions mapping from an n-element set into 0-1 set. For that reason, we require f to be functionally folded, which is a key tool of the UFG hardness result for abelian groups. We define functional folding as follows. The definition of functionally folded f says that for every g-valued n tuples x and y and f mapping r bit strings to g, which satisfy the relation shown on the screen, that is xd is equal to the f of p1d up to the prd yd for every d in n, we have f of x is equal to the f of b1 all the way up to the br times f of y. Although this definition might look complicated, observe that if f is a long code of a label satisfying the conditions mentioned above, that is that pi of L is equal to the bi, then f indeed satisfies the conclusion f of x is equal to the f of b1 up to the br times f of y. We are also using representation theory in our work. Let us start by recalling that the general linear group of C to the power of m, written as GLC to the power of m, is the set of all invertible m by m matrices with complex coefficients, with group operation being matrix multiplication. Then we can define a representation ρ of a group G to be a group homomorphism which maps from G into general linear group. We will not go into details about group theory, but we will instead focus and discuss representation theory on our previously considered non-abelian group S3. One trivial representation is given by a map which maps every permutation to 1. Observe that the codomain here are invertible 1 by 1 matrices. Another representation is given by the sign of a permutation. Once again, the codomain are one-dimensional matrices. Another representation is given by identifying a permutation by a transformation of a plane. Let us explain this by considering a permutation pi which shifts values 1 to 3 to the right, and explain what ρ2 of pi is. We can represent 1, 2, and 3 as vertices of an equilateral triangle, and then the permutation pi is actually a rotation of this triangle by 120 degrees. So we can actually represent ρ2 of pi as a rotation matrix. Representations of other permutations can be defined analogously. Finally, let us remark that in a certain sense, the first two representations are not able to capture non-abelian structure of S3, in particular because GL of C is commutative, that is, multiplication of one-dimensional matrices is commutative. However, the third representation does catch non-abelian properties of G. Representations can sometimes be decomposed into direct sums of smaller representations. And representations that cannot be decomposed are grouped in a set of irreducible representations, which we denote with I rep of G. It will be useful for us to remark that irreducible representations on G to the power of n are actually tensor products of irreducible representations of G. But why do we care about representation theory? Well, in case of our work, we do so because it gives us access to the Fourier analysis of non-abelian groups. In particular, Fourier coefficients are indexed by irreducible representations, and they are defined for any function q mapping from a group G into complex numbers by the expression shown on screen. Fourier analysis remains a powerful tool in the non-abelian setting, and we still have access to strong tools like Parseval's theorem and Fourier inversion theorem. Let us now discuss one of important lemmas which gives us useful information about the Fourier coefficients of functionally folded functions. In particular, the statement of the lemma reads as follows. Let f be a mapping from G to the power of n into G that is functionally folded, and let irreducible representation ρ be non-trivial, that is, ρ is not isomorphic to a constant 1 representation. Given some I and j between 1 and dimension of ρ, let q of x be equal to the ijth entry of ρ of f of x, and let alpha be an irreducible representation on G to the power of n, which can be decomposed as a tensor product of irreducible representations alpha I on G. If for every d between 1 and n, such that alpha d is not isomorphic to 1, we have that the vector p1 of d, p2 of d, all the way up to pr of d is not equal to b, then the alpha Fourier coefficient of q is equal to 0. This lemma is essential for showing hardness of almost satisfiable instances with universal factor graphs, and in particular the motivation for defining this possibly odd-looking q lies in the way we do our analysis. In broad terms, this lemma says that once we exclude trivial cases, each non-zero Fourier coefficient of f will contain information about a label d which satisfies all the constraints pi of d is equal to the bi, where I goes from 1 to r. This will be useful since we work with functions whose Fourier spectrum is concentrated on coefficients corresponding to constant size representations. A different lemma is used for universal factor graph hardness of perfectly satisfiable instances. In particular, our non-triviality conditions for ρ and alpha d from the statement above need to be replaced by a different non-triviality condition which states that dimensions of ρ and alpha d need to be greater than 1, since, as we hinted before, dimension 1 representations do not capture non-abelian structure, and perfectly satisfiable instances are easy to solve for abelian groups. Let us conclude this talk with a summary. Our result is completing the string of results on optimal inapproximability of Max-3-Lin G. In particular, we show that Max-3-Lin G for non-abelian G is 1 minus epsilon, 1 divided by the size of G plus epsilon, universal factor graph NP-hard, and 1, 1 divided by the size of commutator subgroup plus epsilon UFG NP-hard. We also reiterate that our hardness results hold with nicer expressions without constants between variables or inverses. With that being said, I would like to conclude my talk.